Okay, so 27 is kind of a weirdo problem because I don't know, it's hard to picture. A person throws a ball of mass 0.2 kilograms. The ball starts from rest, okay, and then accelerates horizontally and uniformly through a distance of, this is the weird part, almost a meter. So that means that this person, I'll draw a person like this, was like somehow pushing this thing completely, or maybe it's like Superman, I don't know. Something weird. That's supposed to be Superman. Somehow pushing this for this far, which is bizarre to me, but whatever. Okay, till it goes here and it attains a speed, so your initial velocity presumably is 0, and your final speed at the end when he finally decides to let go, or she finally decides to let go of it, is what they say it was 30 meters per second, which is crazy fast. So clearly it is Superman, or woman, or girl, or whatever. Okay, so the average horizontal force applied to the ball by the person's hand is what? Okay, so, yeah. The easiest way to look at this, they're really liking doing this time. Okay, remember, that work is in fact a change in energy, in this case, kinetic energy. So work is a change in energy. Work is also force dot displacement. So let's look at this. Force dot displacement equals a change in kinetic energy. Since we're starting from 0, we're just going to say it's 1/2 mv squared, which is the final there, okay? Final speed, not velocity. We're not worried about which direction it goes. Also, you don't need the dot product, so if we want to solve for this, therefore, F equals mvf squared over 2s. Sorry, I ran out of room. So therefore, or here, I can do that. I think I have room. All right, equals your mass, which is 0.2 times velocity squared, which is 30 squared, which is 900, over 2 over 0.9 meters. Okay, so if you put this into a calculator, calculator, it is going to be 0.2 times 900, because that's 30 squared, equals 180 divided by 2, divided by 0.9, which gives you 100. So yeah, that's your answer, is a D, 100, 427. Okay, so let's look at 28. Okay, this one's weird because it has the fractions. I'm going to attempt to do this in the fractions for you. Just to know the speed. Okay, I'm going to say right now that M is going to be equal to, I'm doing my own weird AP thing, M is equal to 1,500 kilograms. To me, this just makes life easier for the fraction thing. So I'm going to define this as my positive and this is my negative. So I'm going to have my M car, okay, and it's going to be going 4 meters per second this way, and then I'm going to have my 2M car, because that means that it's twice 1,500, which is 3,000. You don't have to do it this way. You can do it in the calculator and then figure out your fraction. To me, this was just easier, but whatever works for you. 3ms, right? Okay, so this is just straight up, and then that's before then they collide into something big that is 3m, because 1m plus 2m is 3m. Okay, so the way I would do this is momentum is conserved here because there's no outside forces. So that's 1, velocity 1, plus mass 2, velocity 2, equals mass 1 plus mass 2 times velocity prime. And then so you bring this over here as be mass 1 plus mass 2. equals velocity prime. So anyway, mass 1 times velocity 1. So that would be like, that'd be m, I'm going to say 4m minus 6m over 3. Okay, so that should give you negative 2/3, right? And that'd be over 3m. And hey, look, your m's cancel out. So that gives you negative 2/3, and we're just looking for speed, so 2/3 meters per second. If you work it out, you get like negative 0.6667. Same thing. I just decided to do it this way because just to show you a different way if you didn't have time to put it in the calculator. If you don't get this, that's fine. If you put all this in the calculator, use this equation, you're good to go. Okay, so I think I'm going to stop this one here.